Okay, so looking at the way that this thing is set up, these are two current carrying wires, a blue one and a red one. I tried to color code it. And if you point let's talk about the one on the right first. If you point your thumb in the direction of the direction of the current, to the right of the wire, your fingers would curl into the page. To the left, they would curl out. And if we look to the right, we have the X's, and to the left, we have the circles. And if you look, the circles get smaller as we get farther away. The blue circles get smaller as we get farther away from the blue wire. And that's an indication to show you that the magnetic field is getting weaker as we get farther away from the blue wire. And if you look at the wire on the left that is red, then you should be okay with the idea, if you take your thumb on your right hand and point it in the direction of the current, that your fingers would curl out of the page to the left of that wire and then would point into the page to the right, which is why if you look at the red X's, as we get farther away, the red X's get smaller from the red wire. And then if we take a look at what's going on, force on 1 by 2, F12 would be the force on 1 by 2. The force that one feels would be due to its own current, which is why it's red. L is a generic length, and B would be the magnetic field produced by the blue wire. So knowing that, the I and L remain the same, but this B field would be generated using the Biot-Savart law, which would be mu naught I over 2 pi d, where d is the length of separation between them. Similarly, if we figure out F21, then we'd have the force that the blue wire would feel would be its own current times generic length times the magnetic field produced by the red wire, which would be, using the Biot-Savart law, mu naught red I times 2 pi divided by d. And the point of this is that these two equations are exactly equal with the exact same variables. And the reason for that is because they are then an action-reaction pair, where they are equal in magnitude and yet opposite in direction. And if you want to know the direction of the force on a current carrying wire, then you're going back to using the equation we have from like F equals QVB, where you would point your fingers in the direction of the current. So if we're going to examine the red wire, you would point your fingers from your right hand towards the top of the page. And you would have to point your palm in the direction of the magnetic field in which the red wire is placed. And the red wire is placed into the magnetic field of the blue wire. So your fingers on your right hand would point towards the top of the page. Your palm would point out of the page, and your thumb would then point to the right. If you examine the blue wire, then your fingers would point towards the top of the page again. Your palm would have to point into the page because red X's mean into the page, and your thumb would point to the left. And so if the currents are in the same direction, the forces are attractive, and if they're in opposite directions, if the currents are in opposite directions, then those two wires would repel each other. Now, looking at the next page, this is Ampere's law. This is effectively what Gauss's law does for Coulomb's law, Ampere's law does for the Biot-Savart law. If you look at the way it shows up on, I have this written on this sheet. This is changed because I'm using some other program. So the equation should be closed integral B dot ds equals mu naught I enclosed. So that should be a mu naught, but it's being changed to an m naught because of, like I said, something within the program. But the important part that we need here is, if you want to know the direction here, basically, instead of having a Gaussian surface, we're going to have an Amperian loop. And so you just imagine a loop surrounding wires. That's what they're doing with that red kind of jelly bean shaped path. And you just point your fingers along the direction you want to go. And as your thumb, if your thumb matches the direction of the current, up, up, then that's positive. Or if it's opposite, then like your thumb is up and this current's down, then we would say that the current is negative. And so if you curl your right hand around the Amperian loop with your fingers pointed in the direction of integration, which just means whatever path you want to go, the current through the loop, the current in the loop is assigned positive based on where your thumb is. I got to stop there.